So thank you very much for the invitation to speak. It's always a pleasure to come to Lumini, and it's always definitely a pleasure to come to an Illustrating Mathematics event. I'm very happy to see all the beautiful things. I should also start by saying that this is maybe a bit of an intermediate talk, so maybe more math and slightly less illustration, but I have pictures prepared, so I'll try and draw those. Please stop me at any time and ask questions. I understand this is quite a broad audience, so it's kind of like a relaxed introduction to, well, curves on surfaces and train tracks. And in particular, there are some interesting illustrating questions which are underneath the hood. And at the very end, I'll actually try and end with a philosophical problem which I encountered about drawing pictures and trying to convince myself whether or not pictures meant mathematics or not. Okay, so, but just to give a bit of structure to the whole thing. This is my outline of the talk. As the saying goes, every talk should have one theorem and, sorry, I should have, as the saying goes, every talk should have one theorem and one joke, and it should be clear which is which. So here we go. This is due to Bell and myself. Suppose that S is a compact connected, oriented surface. So words that are underlined, I will explain what they mean. Suppose that tau contained in S is a train track. So these are the things that I hope that you will grow to love, or at least draw. Then there is an O of n log n, log squared n algorithm that, given a weighting let me call it mu, which is a weighting with integer coefficients on tau, computes the number of components of the curve, the carried curve. I have to tell you what that is as well. Alpha mu. So there is the theorem statement here. It's got 1, 2, 3, 4 underlined words, and I'd like to try and say what all of those things are. Up, sorry. But just so that you can rest easy, this is a very fancy version of the Euclidean algorithm. Okay? So a weighting, as a toy example, you could think that that's a pair of integers. And the number of components of the carried curve, that's supposed to be the GCD of the two numbers. So if you know how to compute GCDs of pairs of integers, then you're already a big step along the way to proving this theorem, although there's more to it than that. In particular, if you think about how you compute GCDs, you will realize that unless you already know what I'm going to talk about, then the algorithm you have in mind takes time n squared. Okay? The standard algorithms for computing GCDs and the ones that you teach to your undergraduates take quadratic time. This n here is the bit sizes of the two given numbers. Okay? It's quadratic time in the given, which is the representation of the numbers, not quadratic time in the numbers themselves. Okay, so I'm going to leave that there for now as a grand analogy, and let me get back to explaining the various words that I've, in my notes I have another remark, which is the theory here has various other applications. For example, we give a n log cubed n time algorithm to solve the word problem in the mapping class group. Okay, but I'm not going to discuss that today. Also, there's an n log squared time algorithm to compute geometric intersection numbers of curves. I'm not going to talk about that either, but they all involve drawing more and more pictures of sort of similar types and thinking about things. Okay, so again, that's just the motivation and the outline. If you know some of the stuff that I'm saying now, then there's an exercise on the board. How many components does that multi-curve have? Okay? And is there a way to figure that answer out, which is better than tracing with your finger? Great, which is sort of exponential time in some sense. Okay, so surfaces. Have genus and boundaries. So let's see, suppose that we have the genus G and boundaries B. So here is G equals 0, B equals 0. The only such connected, compact, oriented surface is the two-sphere. And I have to admit that I wrote this talk, I think, 3 times. And the first time I wrote the talk, I actually was going to talk about what this picture means, but I decided that I should do something else. But I invite you to contemplate the fact that none of these lines represent boundaries, because there are no boundaries, right? And none of them represent holes, because there aren't any. So what is this line doing? That's the visual tangent, right? The I-beams from your eye are tangent to the orange, which I'm trying to represent. And this line here, that's the belt, which keeps its clothing on. Now, this is G equals 1. So now, we still have no boundaries, but we have this, instead of an orange, a donut shape. This is a torus, T2, and let's do G equals 2. So here we have the genus is now 2 instead of 0 or 1. This is sometimes called S2, like so. And so now we can start adding boundary. Oh, and I should say what I was not going to say here in my other talk. The funny, complicated business here where it looks like an eye kind of staring at you, you're actually looking through, right? The donut is here and that's empty space. And so then why is there little curlicues here? It's because some swallowtail cusps, which are combining to form bent sheets. Okay, so this is, maybe instead of talking about that, I should just mention a book by George Francis, which is the topologist's picture book, which kind of explains some of the details of drawing these, these representations of surfaces. They're not actually surfaces because they're just drawings made of chalk in the blackboard. But, oh, and I'm also writing down some of the names, although not all of the names are very common. And then maybe one more. Actually, let's do a couple more because the annulus is good to have. Yes, a question, please.
No, it's not just a remark. Can you use the button to do the center of the board?
What's that?
We have been told to use the button for the central boards.
The button for the central boards. Oh, and these
The boards are too heavy for you.
The boards are too heavy for me. Oh, I did not realize. Okay, thank you. The naming schemes are a bit random for the higher genus and higher number of boundary components. So these are portholes in like jet engines or something, rocket ships. Okay, so maybe that's enough to go on. So there are some surfaces. Always compact, just repeating that. That means that they're bounded, closed and bounded in extent. Connected, don't have two pieces. And oriented. Like so. So that's the first topic discussed. Curves is next. I'm not quite sure why it always wants to go down. Will that convince it to stay up? Again, I kind of cheated, I'm sorry. But I drew this ahead of time. And by staring at it, you can kind of see one of the ways that I cheated. But let me just try and draw another picture. So we have the handle here. And I'm going to cut it open to get a surface here. So what this cartoon is supposed to represent is that if you take the four edges, which are straight, we're not going to do anything to the curved bits, but you take the four edges which are straight and you glue them in opposite pairs, then you get a surface which is homeomorphic to what I've drawn here. Oh, I skipped something. I will put this on pause, my mistake, excuse me. So just a theorem. It's not happy, is it? Suppose STR surfaces, always compact, connected, and oriented. Then S is homeomorphic to T if and only if. Well, so my diagram here is kind of suggesting the only thing that you really need is to know the genus and the number of boundary components. The genus of S equals the genus of T, and the genus of the number of boundary components equals the number of boundary components of T. And another way that people often write this is by writing the number of boundary components, the magnitude of the set of boundary components equals the magnitude of the set of boundary components of T. So this leads to an exercise, which I've now shown you the answer to. You know what? Let's change the exercise. Find G and B4. And so then we'll have a few example surfaces, and I'll draw them on the next board. So my apologies. I'm going to rewrite this on the next board. So let's just have some exercises, since this is a winter school. So what I will do is I will try and draw some surfaces. And again, I'll try and use the various tricks to suggest that they're three-dimensional, but again, they're really just drawings of chalk in the chalkboard. Whoop. Whatever. There, that's fine. And then let's have another one. In fact, let's have two more, but all with the same kind of feeling to them. And I'll leave it to you to give other versions. In particular, George Francis in his book, which I'll write down the name of in just a moment, does a beautiful job with the figure 8 knot. And then I need to add the little trompe-l'oeil business here, 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 and here. So again, there's now two kinds of chalk lines which are fighting each other for preeminence. This is the actual boundary of the surface, and that is visual tangency. So we draw red on this side, and we draw blue on this side. So in each case, the question is, what is the genus? What is the number of boundary components? And in general, you could add, let me actually in some green, give you a zoom in on one of these regions right here. So this half-twisted band is appearing everywhere in my figures. What does that actually look like? Here's a larger version of it. It is going like this, and like so, and like this. And then one side of the half-twisted band is red. And the other half is blue. Or rather, I should say, one side of the half-twisted band is red, the other side is blue. If you take this and untwist the half-twisted band, this is a half-twisted. Then, of course, you will get just a band. Untwist. So I'll take this point here in space and that point there, and I will untwist them in this way. The one on top comes towards you out of the board. The one on the bottom goes away from you into the board, and we will get just something like this. And it's only red, only red. The blue side is now on the back, and you can't see it anymore.
So in your theorem, how should I understand the genus? Can you define genus somehow without knowing the classification of surfaces?
No, yeah, it's cheating, yeah. So you need to know what you're correct. You need to know how to define the numbers without knowing the classification theorem ahead of time. So what you could do is you could glue disks to all of the boundary components, right? And then compute the Euler characteristic. Okay, so question, let me repeat the question. Question, what is the genus? So coincidentally, that's the name of a book, which has got like 50 chapters, very short, and each one is some sort of discussion of what is the genus in terms of either algebraic geometry or topology or Gaussian curvature and so on. So there's many, many names, many ways of, holy moly. Well, maybe they're interested in drawing surfaces. Just C-book of same name. But perhaps just as not a real definition, but definition, theorem, the Euler characteristic of SGB equals 2 minus 2G minus B. Okay? So the Euler characteristic has other definitions, so you could reverse engineer and use this to define the genus. Does that, in some sense, answer the question? Yeah, okay. No. I don't have, there's another definition no. There are many, really what's going on is there's many definitions of, there are many definitions of the genus, sometimes in terms of the Euler characteristic. Yes, a hand.
What does sigma stands for, like in the theorem, in part 2 at the end?
Oh, yes, very good. So above, boundary S is the boundary, the subspace of S consisting of boundary points those points without disk neighborhood, open disk neighborhood. So pictures, because everything should have pictures. So above, I didn't actually define surface. I just drew a bunch of pictures. But a surface is a topological space, which is Hausdorff's second countable, and locally homeomorphic to R2 or the upper half plane. So here is my handle, and if I draw a point right here and a small neighborhood of it, then this is homeomorphic to a little bit of the plane, and there's the point in the interior of the chart. Whereas here, I have my point, which is now a dot instead of an X, and instead of having an open disk neighborhood, it has a half open disk neighborhood, like so. So this is a bit of R2, and this is a bit of R2 greater with the last coordinate y greater than or equal to 0. Like so? Does that answer your question? And you didn't really have a question, you just wanted me to say stuff, right? So I don't need to ask. Other questions? That is very tall. No, stop. You're right, I'm not strong enough for any of this. Okay, so last thing that I promised is there's another book by George Francis. Topologists. Picture book. Okay, so now I think that deals with surfaces. So let me think about the next part, curves. Can be complicated. And so now I will recopy. So here's the handle again. And as I claimed, but it is an exercise for you, this is homeomorphic to the disk with boundary glued together with the following pattern. So the boundary points here will come from the bits that I didn't glue up, which have half disk neighborhoods. So now let me try and draw a curve, which is not too insanely complicated. In fact, what I'll do is I will try and stick to the, so I drew, my curve is going to cross the vertical 4 points, that's going to cross the horizontal in 6 points, and now I'll just connect the dots. So the curve does something like this. And already maybe you see where the GCD is coming from, but let me explain. So here's a curve on a surface, and because of the magic correspondence, there's 4 crossings here, there's 6 crossings here. One greatly expects that this curve, multi-curve, will actually have 2 components. So I don't think that I can draw it here, so I'm not going to even try. But the instruction, the title of the talk is how to draw curves on surfaces, so this is one way to do so. Let me draw a much simpler curve. No, I think that will just get me in trouble. So I will draw this curve here. But I'm not done. I will do this. There we go. Okay, so I claim that what I've drawn on the left-hand side and what I've drawn on the right-hand side are actually homeomorphic. There's a homeomorphism which carries the handle to this. If you cut the handle open, that carries it to this, and this quite complicated looking thing here and this quite complicated looking thing here are exactly the same. And I did it too fast for me to actually be thinking about it, so there must be some theorem, which is telling you why everything is the same. Okay. So, yes. Well, when I cut along properly embedded arcs, but everything that I'm drawing is a embedding of S1 into the surface. Yeah, or embedding of a disjoint union of circles. That's what a curve is. Yeah. So to answer your question, definition, a multi-curve let's call it alpha in S is an embedding. I'll also use alpha for it. Alpha mapping a disjoint union of copies of S1, so there'll be K components here, into my surface S with alpha intersect the boundary of S is empty. Okay, so that's a multi-curve. It is also possible to talk about multi-arcs or multi-arc curves. And arcs are very convenient to cut along, and curves are also convenient to cut along. Yeah, but this is what I'll mostly be drawing in red. Does that answer your question? Yeah. So notice that when you take the handle and cut it open, the curve falls apart into lots of arcs, many, many pieces. So now I think I should regain where I was going, which is I'm supposed to take the simple. Let's take this example to note that embeddings do not cross themselves. So that's a tautology, right? What it means to be embedded is that it doesn't cross itself. But because it's a two-dimensional surface and the curve is one-dimensional, since it doesn't cross itself, when you're drawing a curve, When you go into a region of parallelity, well, you can either turn around and go back, or you can keep going till you come out the other side, and that forces the curve to be quite parallel to itself in various regions. So curves, nicely drawn curves, so nice curves, of course that's a bit vague, must run parallel to themselves. So this is the thing that allows us to produce train tracks. So again, I will just copy that picture twice. Actually, I will do it here as well. When I see stuff that's parallel, I could enclose it in a box. And then what I want to do is I want to take everything in that box and squeeze it down. They're all parallel. Why did I draw 4 things here? I could have just drawn a box with the number 4 on it. And similarly here, and so on. And then what I do is instead of drawing all the parallel strands, I just draw a representative of the box. Okay? And that's how I get train tracks. So let me do the simpler version of that here, where I draw 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. And then I have to choose the boxes. And I'll choose my boxes here. Obviously, there's a choice in the box. And here, and here, and here. And this ambiguity, the choices that I make in choosing the box, that gives me the following train track. And I'm supposed to put weights on it because this strand here contains 6. This one here contained 1, 2, 3, 4, 5, 6, 10. And this one here contained 4. So this process of thickening produce train track. By picking boxes of parallel strands.
Is it your train track picture with other choice of boxes for you? Can you repeat the question?
Sorry, say it again?
In your picture, I would have expected, in the lower right picture, I would have expected the label 2, 6 from it.
This box right here contains 10 parallel strands.
Right, but don't the tracks then have to connect the other way around? The other 4 and 6.
Oh, my word.
You drew the train track with other choice of boxes.
Ah, you know what I did? My bad. Okay, let's try that again. There's definitely a 10 here, right? That's hard to argue with. So I have to put a 10 right here. And there's definitely a 4 here, and there's definitely a 6 here. So I think we should trust the numbers more than the speaker. Yeah. So 6 plus 4 is 10. 6 plus 4 is 10. 6 plus 4 is 10. Ah, God.
Saul, leave it as an exercise. Proximity to the chalkboard.
Yeah, it causes stupidity.
So 6 is right. 4.
I did this one ahead of time. That one's okay. But I'm quite sure that we can do this together.
Bottom 6 should be the left 4.
How about that? This one's not in my notes. This is a simpler one, which would be easier for everyone. And of course, it is better because people learn stuff. Okay, so there's the example. And one learns maybe not to do things that aren't in your notes, but also not to use all the boards. Wow. Let me ask a quick question, which is, where's my time at? Who's in charge of keeping track of the time?
You still have about, well, we started it later, still 10 minutes?
10 minutes. Right, so let me just give a quick fake definition of train tracks. Are let's say tau contained in S, locally modeled on. So we said surfaces were locally modeled on bits of the plane and bits of the half plane. So this is a graph. So I'm going to give the local models as follows. One local model is, it's just an edge. It's an edge of the graph. And the other local model is it's a vertex of the graph. But since they're train tracks, these will be called switches, although they should be called points, at least in American English. And these will be called branches. And we've already seen a few examples, but let me draw one more. So here again is the handle, and here is a train track in the handle, like so. There's actually one more rule for constructing train tracks, which I will just quickly mention, which is kind of an Euler characteristic restriction. And this is required to make things work out. Also, if R is a region of S minus tau, strictly speaking, I need to take the compactification in the induced path metric, then the index of R, which is defined to be the Euler characteristic of R minus 1/2 the number of cusps, and I'll draw a picture, must be less than 0. So perhaps thinking about that sort of picture, regions. So here are some bad regions. This is the monogon. Here's the nullgon. Here is the annulus. And finally, the bigon. So I claim that those are the all of the regions possible where the index is non-negative. Well, I guess if the train track was empty, there'd also be the sphere. So maybe in the interest of leaving time for questions, I should finish with one more remark. No, I really should draw the inverse of the process. Okay, so I'll do that next. Definition: a weighting mu from the set of branches is two properties, non-negative and satisfies switch conditions. So what is that? Here is my bit of train track. So there's three branches here, A, B, and C, well, half branches which are coming into the switch. And each one of them gets a weight. We require that the weight on A, what comes in, must equal the sum of the weights on B and C. And so one way to think about this is if these were integers, positive integers, then the number of strands that comes in has to be the number of strands that goes out. And this was what I was getting messed up with and what John so kindly pointed out, right? If there are 6 strands coming in and 4 strands coming in, then 10 strands have to go out the other direction, like so. So maybe I'll just draw one final cartoon. Maybe I have 1, 2, 3, 4, 5, 1, 2, 1, 2, 3, and then I have my green boxes like so. So once you've chosen the boxes, that kind of is telling you what the structure of the train track should be. A curve that's produced this way, let Vz tau be mu from b tau to z weighting. Let alpha mu be the resulting multicurve. So what we're supposed to do is we're supposed to look at the weights and we go backwards, right? We produce boxes, we draw parallel strands inside the boxes, and then we connect up the ends in order to get a curve. And so I've kind of done, that's not happy. In the middle board there, you can maybe just barely see that you can either go forwards, take parallel strands and produce numbers, or you can go backwards, take numbers and produce parallel strands. This then is the correct way, or a correct way, one way to draw curves on surfaces. Don't actually draw the curves at all. Instead, draw the train track and put weights on it. And now we can return to the theorem everything has now been defined. If I give you the weighting, then you should be able to find the number of components of the induced carried curve. Yeah? So one way to do that is to just draw the actual curve, the whole thing, the parallel strands, and then put your finger on it and start following along. Okay? But that takes exponential time in the givens, which is the train track with the weights written in binary. Okay? So that's a very inefficient way to think about curves on surfaces. So there is a better algorithm, which is one here. Let me just, yes, a hand. The weights are non-negative integers when I put a z here. But if I put an r here, then the weights are non-negative real numbers. And then when you do the procedure, which is draw boxes, put strands in them, and pull things apart, you don't get a multi-curve, you get a lamination, a measured lamination, okay? So in some sense, the integer weightings are the integer lattice points inside of some larger space, which is the space of measured laminations, okay? And just that I said I made the choice of the boxes, that tells me how to pinch down, right? There are many ways to represent a single curve as a weighted train track. There are also many ways to represent a single measured lamination as a train track. This gives train track coordinate charts on PML or ML or PML, depending if, anyway. Does that answer your question? Okay, so last collection of pictures. Deep inside the proof of this theorem or another theorem, I found myself drawing lots of little bits of train track. In fact, what I want to do is I wanted to say not just how many components does a curve have, but if you have two weightings on one train track, then you might want to ask those two curves, how many times do they intersect in geometric intersection number, which I didn't define. And what you want to do is you want to like split the train tracks and simplify the intersection patterns. And I wound up with a proof which had like 100 little pictures that looked like this. So the philosophical question that I'll end with is, I knew that the theorem was true because I drew all the pictures and I hadn't missed any, but maybe I had missed one. And I wasn't really feeling like I should draw 100 little doodles in the paper, but I was prepared to do it. And my collaborator, Mark Bell, said like, well, no, we shouldn't draw them by hand. We should write like some little computer program to generate the doodles for us. And then he said, but really, once you've written the computer program to generate the doodles, the computer program, it doesn't work with the doodles. It works with little representations. So the representations have the following form. There is a R, there is a dash, there's a B, there is a B, why is it red? There is a corner, there is a R, there is a B, there is a dash, there is a V for cusp, because it's pointy, right? The computer program works on the inside with these strings, right? All these things are disks, so it's just a cyclically ordered string. And then you like concatenate strings and break them apart. So we could just write down the strings, but in fact, what Mark said was, what we'll do is we'll write down the Python program which generates the strings. And since the Python program terminates, that means that we've drawn all the doodles. So he replaced my hours and hours of work with a Python script, which is what showed up in an appendix to the paper. So thank you for your attention.
Further questions?
Can you say again what is n in the theorem?
Yes, so n in the theorem is the number of bits required to represent the weighting. So a weighting is a function from the set of branches. There's only finitely many branches of the train track. For example, here there's like about 10. Yeah. In every train track, in a train track on a surface, there's at most like 18G branches. And the reason why there's an upper bound on the number of branches in terms of the genus and the number of boundary components is because of the negative Euler characteristic that I imposed here. Okay, so there's a fixed number of branches. That's a constant. It only depends on the surface. For each one of those, we write down a number in binary. The total number of bits required, that's n. Right.
So yesterday you were worried about getting replaced by AI, and now you're worried about being replaced by a Python script. Is that where illustration goes when it turns into a proof? It turns into a Python script.
Well, I suggest that you think about proving this little theorem here, right? And enumerate all the regions which have non-negative index. And it's just these 5 pictures. And eventually you draw the 5 pictures and you say like, okay, yeah, I'm convinced. Or maybe it's 6 if I missed one, right? But then you draw the pictures and you're convinced. But then you ask yourself like, okay, is that really a proof? How much formalization do I need, right? And so there's some place where like once you have enough doodles, maybe it's like you need to formalize things a bit. In fact, Mark's Python script doesn't draw the 97 doodles that I drew because I was using various symmetries along the way. It draws like 368 or something. I don't remember the exact number. But it doesn't matter how many it draws because it terminates, so the theorem is proven. Yeah? So which one is more convincing? Me drawing lots of little pictures, each of one of which means a little something, or like staring at the Python script and, well, say it terminated, so I guess there's a question of how the meaning connects with the formalization, or how the meaning connects with the pictures, for example, right? Someone who's not familiar with these pictures, which is probably several people in the audience, I apologize, like the diagrams of the surfaces were okay, but then when I started cutting them into pieces, like, wait, which one is which? And the exercise right there, it's like those generally have genus 0, 1, and 1, but it's just not easy to see that. Yeah. Right, why do these pictures have genus this, that, and the other? So I don't think that's answered your question, but I would like not to be replaced by AI, but being replaced by a Python script seems a little worse, I guess.
All right, if there's no further questions, well, we can always have further questions during coffee break, but let's thank Saul again.